An important thing that also has been said before, but is always good to remember, is that you may have concentration zero in this table. What does it mean? That the protein was not present? Not always, especially also in LFQ. It could be that the protein was below the threshold. So it means that the protein was present in your sample, but was not at a high enough quantity to be identified and quantified. So we have two types of quantification. Again, we have the same table here, simple proteins, samples. There is the absolute quantification, so it's the total amount of proteins that you quantify in one sample, and it's the yellow bar here. Then we have the relative quantification, that is instead the quantification of a specific protein across all the samples. And usually this is the one that we are more interested in because we want to compare different samples, and so we want to compare the relative quantifications. Again, you already seen this image, but yeah, you can do quantification with MS1 labeling, MS2 labeling, but for this specific talk, we will focus only on label-free quantification. In MaxQuant, there is this algorithm called MaxLFQ that analyzes LFQ data. And it was initially developed for DDA, but now 3 years ago, was also improved for DIA. And also tomorrow in the DIA section, there will be Jürgen that will show you a major improvement that's been done in MaxLFQ algorithm for DIA specifically. So hopefully now MaxLFQ works very well also for DIA data. So probably you already know why doing LFQ quantification. Well, the first good reason to do that is that it's cheap. You don't have to buy reagents, specific reagents like labels. You can theoretically do as many samples as you want because you're not limited to the type of label that you use. So theoretically, if you have enough money and enough time, you can really go up to thousands of samples together. Another important thing is that proteins that you analyze with LFQ are chemically identical. They are not labeled. So if you remember before, in the label quantification, there were some issues about the peaks that you get. They were lower for specific markers. You don't have any of these problems for LFQ. And also you don't have any batch effect due to the label that you use. And also last good thing is that you have a higher dynamic range. And also you can parallelize all your experiments because you run in different LFQ mass spectrometry runs together, so you can also parallelize your experiment. So there are many good reasons why to do LFQ, but as you can imagine, there are also some side effects. And the major problem is that, as you can see from this image, when you do, for example, in this case, SILAC again, you have a single run and you have your two samples here in a single MS run. When you do LFQ, it's not like that. You have to run multiple MS runs. This brings up to many other, to some issues. Like, for example, we have different retention time between all the different runs that we do, as you can imagine. Retention time changes, so then this will affect the data they will get. Every time you do an MS run, you're not sure that for MS2, you will take the same precursors. It could normally happen because you're running different MS runs. So probably maybe in the first one, you select certain precursor. In the second one, you select others. If you then pre-fractionate your data, you then create another level of complexity that will cause then your samples to be different. So not to be analyzed together. So then you have to take in consideration these differences when you compare the data. So these things will make your data uncomparable together. And then also we have just a pure stochastic case that intensity may vary for who knows for which reasons. Maybe it was just a bad day in which you do the second MS run and then your data are totally awful, and then you have very different intensities. So how to solve these problems? All these things that I will show you right now are already done in MaxQuant. So you can tweak the parameters to then change the things, but usually when you select Max LFQ, the software will take care of all of this already. So you already seen this image. Probably now you know it very well. But let's go back to it again. You have here the retention time and the retention time difference between two runs. As you can see here, it has this wheel shape. It should be all like a nice line here on 0 if you want actually to compare these two data sets. So what the software does then creates this curve, taking care of the difference between the two runs and correct for this batch. So at the end, the result that you want to get is something like this. Imagine that here we have multiple different runs that has been plotted together in a scatter plot, and this was after the retention time was corrected. As you can see, they're all linear, nice done. So now we can say that retention time is similar for all these runs. Again, if you have two unaligned runs, you cannot compare them. So what you do, you align them, but on the top of that, as was said also before, this allows you to get some information, some further information from the MS2. So imagine that we had this peptide in MS1 that has been fragmented in run number 1, but not in run number 2. So we know that the two MS1 signals are comparable, are similar. So then we can use transferred information from the MS2 from run 1 to run 2. And then we can say that we identified that same peptide in both of them. So it is a general idea to then increase the amount of peptide that you analyze in your different runs, so to make them more even together. But then there is a problem that you may prefractionate your data. And because of this, you may have different, your peptides may occur in different fractions across your different MS runs. And also this must be, this problem must be solved. And how to do this? Then there is the normalization. Just as to quickly show you, to make a simple example on how normalization works, let's see these people here. And you want to say, who's the tallest person in these two groups? Well, you will first say that probably is this one. But then you have to take care, or you have to take in account the background to see how this person compares to the background. And this is done through normalization. So the idea is then that all the ratios that you have between this person and the background, and also this person and the background, must be centered at ratio 1. So the ratio between the two things must be equal. 0 if you work with logarithmized data. So usually you logarithmize everything, so then the ratio will be 0. How to normalize the data? Well, if you have single shot data, so you just do for each one of your sample a single MS run without prefractionating it. It's very simple. You don't need to do any fancy things. You can just then use the median correction. As you can see from this very simple example, we have these two distributions that are normal. That's a good thing. But we see the median is not in the same spot. So we cannot compare these two things. So what do? We just subtract the median. We do the median correction. And now we see that the peak of the distribution is close to 0 in this case. So now they are comparable. Super easy for single shot data. But we may work with prefractionated data. And here then normalization becomes a bit more difficult. So let's imagine that we have this peptide P, that in this table you can see you have the peptide found in the sample fraction, sorry, these are samples, so in sample A, B, C, and we found it in different fractions. In this case, for example, it is fraction 5, 6, and 7, and here There are others. And here, for example, if we have only 2 fractions, it is quite kind of a mess. The idea is that then every single of this fraction should have a normalization factor, so a number, that will be multiplied to its intensity and will make then all the intensity comparable together. So it will make these differences disappear. The best thing would be to have, for every fraction and every peptide, a different normalization factor. And we can see something like here, for example. We have the intensity for peptide P, and we have intensity in fraction 5, 6, and 7 multiplied by the proper normalization factor for peptide in sample A, for sample A in fraction 5, 6, and 7. And then back again, we will do for the sample B, and then we do everything. And it is summarized here in this table, as you can see. Then every single spot where the peptide was found as its own normalization factor. But then we don't have only one peptide, we have several peptides. So what we do, here we have another peptide with another distribution through its fractions, and we do the same. Again, this is the intensity for peptide Q with its own normalization factor for every single fraction, for every single sample. And here is summarized again in the table. How to calculate this normalization factor then? I just named it, but I didn't say anything about it. So let's recap again. We have our intensity here with their all normalization factors. And here we want to reach the point in which we have one single normalization factor that takes in consideration all the normalization factors for all peptides for all fractions. So all of these n's that has been calculated through the different peptides. So finally, how it is calculated. So you take the intensity from the peptide P and the ratio in fraction A and B. You then square that and logarithmize. And you repeat that for every single fraction where peptide P, every single ratio from fractions where peptide P appears. As you can imagine, there is a lot of calculation then to do. And in this case, once you've done this, you will have your normalization factor for peptide P. And then here, for the total normalization factor, you take all the normalization factors that has been calculated for all the peptides, and you minimize the function, and then you get the result. Is it clear? Kind of. As you can imagine, this requires a lot of time to be calculated, especially if you have a very large data set. So there are ways to then reduce the time that max LFQ requires to get your output, but we will see then further on in the presentation. So this, just to recap the idea of what normalization means, is that, remember here the same example of people that we had. They were not comparable. And now, thanks to the normalization factors that have been calculated from all peptides in all fractions, now you see the background is comparable, and we can say that this person actually was not taller. It's just equal. So in these two samples, there are no changes. But we are talking only about peptides. What about proteins? So imagine that here we have this protein that has been identified through these different peptides. This, of course, is one out of the many possible proteins that we can find in a protein group. So just to simplify it, we put here just one. So we just create a table with all our samples and the peptides where they have been identified. And then we compare the ratios. So we do ratio between sample A and sample B, and we take in consideration all the intensities here of the different peptides. This is done when you do minimum ratio count number equal 1. This is a parameter that you will see also tomorrow in the MaxQuant practical part. That is kind of important also because it allows you to then choose between quantity over quality. I explain now. For example, this happens when you do minimum ratio number 1. So you then take all the ratios for across all samples for all these peptides. But if you then instead use minimum ratio count equal to 2, then it means that you will do the ratio between proteins only that have at least 2 peptides, the same 2 peptides across 2 samples. So, for example, we have sample A and sample B. As you can see, they have both peptides 2 and 6. So their ratio can be calculated. And here we have all these green ratios that can be calculated because they have at least 2 of the same peptides. But then if we then consider sample E and sample F, they don't have same. They are only these peptides in common, but the others are not. So you don't calculate the ratio there. So in this case, you will say these 2 proteins, this particular protein, has not been identified. Has been identified, but will not used for the quantification between the 2 samples. So what's the meaning of this? I mean, if you use a minimum ratio equal to 2 or higher even, you're more sure about your data. So you will get more reliable quantifications. If you then instead keep the ratio equal to 1, that is right now the default parameter. If you use an older version of MaxQuant, you will see that instead the default parameter was 2. If you use 1, you will then quantify all the proteins, even if they have only 1 peptide. So you will get more proteins, but it may be in that case that your differences between those proteins that has been quantified only by a peptide is just because of an error, rather than you're really sure that it was because of a biological reason. So just then, simple representation, we can see the intensity profiles here. So we have all the ratios and the profile of their intensities. And as you can see here, since we consider minimum ratio equal to 2, F doesn't have does have 0 here in the intensity profile. But there is also another problem. So many times you may have large ratios. It means large ratios. So in 2 samples, you identified a lot of peptides, and in another one, very few. So you have a lot of feature in one and very few feature in the other. When this happens, usually these features are not in common. So you may end up with a ratio that you cannot compare because there are not enough peptides that are in common. So there is this algorithm also in MaxLFQ that stabilizes for large ratios. So in brief, it takes the intensities of these 2 ratios of the 2 samples, and then it sums this intensity and then estimates the differences between the 2. So then in this case, you can, as you can see from this image, you can then bring up some information from, for example, the sample F, where you lost your data due to the minimum ratio count, but you can still bring it up, making a comparison between all intensities of the peptides here and the peptides here, even if they are not the same, even if they don't have the minimum ratio count that you need. But this is usually done only when you have large ratios. And usually the program by itself recognizes the large ratios when the number, when the number of features in common between 2 samples is very low. So when you have a lot of features in one and very few features in one, and they are not in common, then it uses, the program uses the total number of features between the 2 samples. So when it sees that the number of features is very different in one sample to the other, then it considers that as a large ratio and applies this. So MaxLFQ, when it was published, was also tested for its accuracy. And one first type of benchmarking was done with small ratios. So how it is done? Usually, this is a very typical experiment that you do. In this case, you see we have human cancer cells and bacterial cells, and then they are in mixture, known mixtures, in this case of 1 to 1, and here 1 to 3. And what you do, you put all these proteins together, you do a mixture, and then you sequence them in the mass analyzer, and then through MaxQuant, you tell the program that you have 2 different species, and then you compare the output that you get. And you expect to find the ratios between all the proteins that have been identified very similar to the initial ratio that you use in your sample. So something like here, you expect proteins to be quantified equally. Here, you expect instead a ratio of 1 to 3. And what was done was, yes, those ratios were actually identified, and proteins were at those expected ratios. So we could have said that with small ratios, the algorithm worked. But what about instead when we have large ratios? As I said before, there is the function stabilized for large ratios. Well, also that had to be tested. So the idea in this case was to do, again, a mixture of proteins. We have a background that is coming from bacterial proteins. And then this UPS1, that is a group of protein, actually 48 human proteins. And they are in ratios, they change tenfold. So there were 4 proteins in this mixture, there were 4 proteins that were changing with a ratio of tenfold. So what I mean, you can see here from this graph, we had our background here that is at 0 because it's not changing through the different experiments. So it is good that it's there. And then we have this UPS mixture of protein that here it's logarithmized. So, but we can see that the difference between these 4, sorry, more than 4 actually, but these proteins were more than 10, was around 10 here, the difference. And then also here, since we have a very small ratio of protein, we can see that they are not linearly grouped together, something like here. As here, they have a higher quantity. So they all are in a nice lines. We can identify them properly. Here they have more noise because the ratio was very small. But still the program was able to recognize that it was this group of protein was at least 40 times lesser present than the background. So again, we can say that in this case, again, Max LFQ worked also for large ratios. Then also a question before was asked about missing values. So imputation, so when you solve the problem of the retention time, when you put together then MS2 runs using the information from MS1, you're not actually imputing the data, you're recovering some data that you may have lost due to issues. In this case, instead, even if you do this, you still may have a lot of missing values. That's always a problem, especially also with LFQ. So what you do is the imputation. You will see this in the per-sales tutorial on Thursday. But just to explain you quickly what imputation means, so we have this experiment. Just to show you one thing, you see here there is an S1 and ES1 and ES2. This means that these are the same data, but analyzed with minimum ratio 1 and minimum ratio 2. And as you can expect, then we have a lot more protein in minimum ratio equal to 1. But anyway, when after you see there are still a lot of missing data here. So what was done then was the imputation. And when you impute your data, you create a distribution of all your data. And then you expect that those proteins, those peptides actually, were coming from low concentration. So you then select only values from this part of the curve, because you're quite sure that probably if they had high concentration, you would have found them. But since they have not been found, they were probably because they had a very low concentration. So you impute data only from this part of the curve. As you can see here, then all these gray dots disappeared with imputation, and they're all dots with the low quantity. Lastly, as I mentioned before, calculating the normalization factors for fractions and all your samples, it might require a lot of time. So if you have single shot data, it is totally fine. Let's repeat it again. We have the median centering, median normalization. So that doesn't require a lot of time to be calculated. It's fine. But the problem is then, again, when we have fractionated data. So you may have a lot of fractions and a lot of samples, and this may require a lot of time if you then calculate the normalization factor for all the peptides. So there is another algorithm in Max LFQ, and it's a parameter that you can tick and say yes or no. You will see also that tomorrow. And that allows you to make it faster. Indeed, it's called fast LFQ.